In this PowerPoint, we're going to talk about energy. All right, so the topics we're going to be discussing are going to be work, kinetic energy and the work energy theorem, gravitational potential energy, spring potential energy, systems and energy conservation, as well as power. All right, so to give the definition of basically any type of energy, energy is going to be some sort of work that's going to be done with a force over a distance. So the force and distance are going to be the two important things when you're talking about energy, as well as this angle. Actually, that angle is going to be important as well, because only a net force that's in the direction, or specifically a force that's in the direction of the displacement, is going to produce work. A force that's opposing the direction that you're displacing is going to do negative work. So that's positive work is where it's in the same direction, negative work is when it's in opposite directions. And if you have an angle here, then the perpendicular component doesn't do any work. So just that component that is either parallel or what we call anti-parallel, meaning it's parallel but in the opposite direction, is going to do any work. So that is where we get this work equation, where the force times distance times cosine of the angle, and that angle is just referring to the angle between these two vectors right here. And that gives me work is going to be a scalar. All right, so it's going to be positive and negative, but what the positive and negative actually mean with a scalar is whether it's increasing or decreasing. So the amount of work we put into the system, if we got a positive work, then that means we're putting energy into the system. If we do negative work, that means we're taking energy out of the system. All right, so what are the correct units for work expression in SI units? Go ahead and answer this. All right, so if you think about the work is going to be equal to force times distance. Cosine of theta doesn't have units. So force times distance, that's going to be newtons times meters. And a newton is a kilogram meter per second squared. So a kilogram meter per second squared times meters gives me kilograms times meters squared divided by seconds squared. We never write it like that. That's actually going to be a unit that we're going to call joules. All right, so our units are going to be in joules for work. So let's figure this out. It says how much work is done by the movers who horizontally pushing a 160 kilogram crate 10.3 meters across a rough floor without acceleration if the effective coefficient of friction is 0.1. So if we're moving at a constant speed, then basically what we're going to do is we're going to look for the force of friction, and that force that they're applying forward is going to be balancing that force of friction. So go ahead and try this and see if you can figure out what the work is being done here. All right, so we start with our free body diagram. We got the forces that are acting on this object. We got a forward force that the movers are applying, and then we got the backward force of friction, the upward force of normal force, the downward force of gravity. So we can use Newton's second law in order to figure out what that force is, the force that the movers are pushing with. That's going to be equal to the force of friction. All right, so coefficient of kinetic friction times normal force, since we're dealing with a horizontal surface, and that means the upward force of normal force is going to be equal to downward force of gravity. So we can effectively go ahead and put that into our equation. And what they did here is they put the negative in there because that's the direction of the force of friction. But what actually happens is we have cosine of theta here. Right, so cosine of theta, that is going to give me cosine of 180 degrees because friction is in the opposite direction. Now, in my opinion, they're a little sloppy with their notation here because really that amount of friction, the amount of friction is going to be in the same direction of the displacement. So really, the negatives are just abundance of them, and it's unnecessary. But we get 0.5 times 160 times 9.8. That's going to give us our force of friction, which is equal to the forces that the movers are pushing with. And then we multiply by the distance, which is 10.3. And that gives us a total of 8,075 joules. Again, joules is the units that we have for work, or basically any type of energy transfer. And if you think of any type of energy transfer, there's always a force over a displacement. Every single energy transfer has a force over displacement. All right, so can work be done on a system if there is no motion? Go ahead and answer this. All right, so if we don't have any motion, think about that. If we don't have any motion, then that means we don't have a displacement. And with no displacement, you're not going to have work done. So it's either going to be C or D. Let's see, C says that since the system is not moving, there is no energy. That's not necessarily true. There is energy. You can have potential energy, gravitational potential energy. You can have spring energy. You can have a variety of types of energies. But that doesn't mean if there's If there's no work being done, then that means there's no transfer of energy. There's no change in energy. So D, no, because of the way work is defined, that's what it's going to be. D is going to be the answer on that. So the next problem, it says an object falls with a gravitational field. Okay, so we're talking about the force of gravity as it falls, and as the object falls, that force of gravity is doing work on the system. All right, so we got a force of gravity times the height, so that's a mass times gravity times the height, and that gives the work that gravity is going to do. Now that work that gravity does, if we actually lift this object up to that point, then we know how much gravity will do by taking mass times gravity times that height. That's what gravity will do. But if we have it up here, then what we call that energy gravitational potential energy, because energy, the gravity hasn't done that work yet. However, it has the potential to do that work. So we call that gravitational potential energy. But if you want to figure out how much work gravity does, you take the force of gravity multiplied by the change in height that it goes. All right, so that's going to be the work for gravity. All right, so a 50 Newton object is lifted 2 meters vertically and is being held there. How much work is done by holding the box in the position? All right, go ahead and answer this question. All right, so if you think about this, holding the box in this position, that means you're not changing your position, which means you don't have a distance or a displacement. Therefore, you're going to have 0 joules of transferred energy. Now, if you take that 50 times 2, that gives you 100 joules. So you do, while you lift it, you do increase the gravitational potential energy by 100 joules. But while it's being held there, there's no transfer of energy, so it's going to be 0. So work is done by forces that with opposed direction of motion. These are going to be negative work. So friction, for example, oftentimes does negative work. Sometimes it does positive work, like the wheels on your tire. As your tires turn, they push against the ground, but the ground pushes it forward, and that friction actually does work. That actually moves your car forward because there's a force over a displacement. But a lot of times when things are sliding, a lot of times sliding just means that an object is going to slow down, which means it takes energy out of the system. All right, so centripetal forces never do work. That's because centripetal forces are always perpendicular to the distance. So as the object goes around in a circle, it's going to be the distance that it travels is going to be perpendicular to the centripetal force. So the force and the distance are actually going to be perpendicular to each other the whole time. All right, so does a centripetal force acting on an object do work? All right, we just answered that. No, it doesn't do work because the force and displacement of the object are going to be perpendicular. So B should be the answer. Next question, it says friction acts on an object. So as the object is moving forward, we do have friction. So the question is going to be, how much work is friction going to do to slow this down? All right, so as it moves, the work that friction does is going to be equal to the force of friction times D, and they throw in this cosine of theta, but really you know that the two are going to be opposite each other, so you can go ahead and just put in a negative. And to be quite honest, I would rather just put in a negative, knowing that work is going to be, or energy is going to be taken out of the system. It's going to do negative work, but they like to throw in the cosine of theta just to make sure that you understand that when you have, displacement this way, and then your force is in the opposite direction, then those two are in opposite directions, being 180 degrees. All right, so the force of friction is going to be equal to the coefficient of friction times normal force, which this on a level surface is going to be equal to mass times gravity. We'll go ahead and plug that in, and you get your the work that friction does. So it's going to be negative mu times mg d. All right, this one, the area under a curve, a force versus position graph represents what? Okay, so we haven't really talked about this, but hopefully you know that is going to be equal to work. Because if you think about force versus position, a force, that's the y-axis, the position, that's the x-axis. So if you have a constant force for a certain amount of displacement, then the area is going to be the height, which is the force, times the distance, which is the the x-axis, and that's the width. So you multiply those together and that gives you work. It's basically a distance times a force. Now the cool thing about this is if you have a changing force, a force increases and decreases, then the area is still going to be equal to the work. You can't just take force times distance when you got a changing force, but if you plot it on a curve and then take the area of that curve, what we call the integral of a force versus position graph, a force versus distance graph, that will give you work. That gives you the amount of energy that is being transferred in that scenario. Next question, on a plot of a force versus position graph, what represents the work done on for the force? All right, obviously that's going to be C, the area under the curve, which we call the integral. That's what's going to give you the work being transferred. All right, so moving on, we got a force acts on an object as it moves forward. So we have an initial velocity here and we have a final velocity here. So you're going to see what happens here, but let's go ahead and do the work that's being done. The work is going to be equal to force times distance, but we're going to use this equation too. Now, I want you to keep something in mind. You have acceleration and distance here. Okay, well, net force, net force is going to be equal to mass times acceleration. So mass times acceleration is force, and then if you multiply by distance, that gives you work. So we're actually going to use this equation. You're going to see what happens with this, how it produces a change in motion, because work does produce a change in motion. All right, so let's get there. So we got net force equals mass times acceleration. So acceleration is going to be equal to force divided by mass. All right, so let's go ahead and plug that into that equation right there. And we get final velocity squared equals initial velocity squared plus 2 times the force divided by mass times distance. All right, so we isolate that force times distance, which means we get the initial velocity squared to the other side, we subtract, and then we divide by 2, then we multiply by the mass, and we get this right here. All right, so on the left-hand side, we have work. On the right-hand side, we have this mass times final velocity squared minus initial velocity squared divided by 2. That's actually going to be something that we call kinetic energy. So we distribute that mass to each one of these terms. We distribute the 2, so divide by 2, and you see that we have the work is going to be equal to the mass times final velocity squared over 2, 1/2 mass times final velocity squared, minus 1/2 mass times initial velocity squared. And mass times final velocity squared divided by 2, or mass times velocity squared over 2, is a kinetic energy. So 1/2 mass times velocity squared is kinetic energy. So a final velocity squared and then initial velocity squared, that gives you a final minus initial. So it's a final kinetic energy minus initial kinetic energy, which we call a change in kinetic energy. So the amount of work done is going to be equal to change in kinetic energy. All right, so work equals change in kinetic energy. Now keep in mind, the kinetic energy has to do with the mass of the object as well as its velocity, the mass and the velocity. All right, so a baseball traveling at 32 meters per second moves a fielder's glove backwards 25 centimeters, the ball is caught. What is the average force exerted on the ball on the glove? All right, so take a second and see if you can figure out what that average force is. All right, so there's actually multiple ways of doing this, right? You can define average force. You can find the acceleration multiplied by mass, and that will give you the force. So you could take your final velocity, your initial velocity, which is 32. Your final velocity is going to be 0 because it's being caught, and then the displacement. So you can use final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Solve for your acceleration, multiply by mass, and that'll give you the force. Or you can use the work equation, which is actually what we're trying to get to here. The work theorem, or the work energy theorem, says that work is going to be equal to change in kinetic energy. So that means that the work done, which is force times distance. Now keep in mind, 27 centimeters, that needs to be converted to meters. Base units for mass or for distance is in meters. Also, the mass is in grams. That has to be in kilograms. All right. So Isaac Newton was the one who decided that kilograms is going to be base units for mass. I know it has a prefix on it, but he's really smart and legendary, so therefore we go by what he said. All right, so you got to convert that to kilograms. All right, so the force times distance, that's going to be equal to the final kinetic energy minus the initial kinetic energy. Notice they put 0 for the final kinetic energy because the final velocity is going to be 0. So anything times 0 gives you 0. Minus the initial kinetic energy, which is going to be the mass, 0.14, times the velocity, which is 32 squared, divided by 2. All right, and then to find the average force, you divide by that distance, which is 0.25, and that gives you your average force is going to be negative 287 newtons. And hopefully that makes sense that you're going to have a negative force because it's slowing down, right? You're taking kinetic energy out of the system. As energy leaves the system, it's a negative change in energy. So if you look at the speed of an object, that can tell you essentially how much what's happening to the energy. All right. Now this force for this equation refers specifically to the net force. It has to be the net force. You can't take an individual force times distance and say that it's equal to change in kinetic energy, because if you got somebody pushing forward on an object and friction pushing against it, then the net force is 0. And if you have a constant net force of 0, then that means you're not going to change your velocity. You're not going to change your kinetic energy. So where work is going to be force times distance, you can figure out the force times distance, the amount of work that a single object does by taking its force times distance. This equation does not deal with just a single force. It deals with the net force. All right, so the average force on the ball is going to be equal to 287 newtons to slow it down. All right, so what is the quantity 1/2 mass times velocity squared? What is that? Go ahead. All right, so 1/2 mass times velocity squared, that is kinetic energy. All right, so if the kinetic energy of an arrow is doubled, by what factor is its speed increased? Okay, so if we increase the kinetic energy, how does that affect the speed? If we increase the speed, how does that affect the kinetic energy? Well, what you have to do is you have to look at the equation. What does the equation say? All right, so if I double the kinetic energy, that means I double the left-hand side. So what would I have to do with speed in order to get a double total kinetic energy? Well, since speed is squared, then something squared has to equal 2. Now think about that. If something squared has to equal 2, then that means that something needs to be the square root of 2. So kinetic energy is mass times velocity squared over 2. In order to get twice the kinetic energy, then that means your velocity, okay, we have to absorb this 2 into the velocity, which means it's got to be the square root of 2. So the new velocity would be equal to the square root of 2 times the original velocity. What if the speed of the arrow is doubled? What happens to the kinetic energy if a speed of an arrow is doubled? So we're talking about an arrow that's moving. As that arrow, the speed is doubled. What happens to kinetic energy? All right, so kinetic energy is 1/2 mass times velocity squared. So if we double the velocity, that velocity is squared. So doubling the velocity actually quadruples the kinetic energy. All right, so now you have 4 times the kinetic energy. Now what's interesting about this is if you're driving down the road and you're going a certain speed, let's say you're going 30 miles an hour. All right, you hit your brakes, it's going to take you a certain distance to stop. All right, so force times distance, that's your work being done in order to stop you. Now, if you double your speed, if you go 60 miles an hour, notice that you're not going to have twice the kinetic energy, so you wouldn't go twice the distance, you would actually have 4 times the kinetic energy, which means you have to have 4 times the distance for that force to stop you. All right, so that's kind of interesting that if you're driving down the road, you double your speed, it's not going to be double the distance that you need to stop. It's going to be 4 times the distance that you need to stop. All right, so that's why a lot of times they tell you to slow down, essentially, because it takes more stopping distance than you actually think, because of the energy being not just not linear, but squared. All right, so work done is equal to the change in kinetic energy. We just said that. So if work is positive, that means that energy is going to increase. If work is negative, that means energy is going to increase or decrease. So an easy way to look at this, you can't see energy. That's the thing. You can't see energy. But what you can see is you can see something manifested about that energy. For example, kinetic energy. You can't see kinetic energy, but what you can see is you can see the speed. So if you want to know if the energy is increasing or decreasing, you need to look at the speed. All right, so if the energy or if the speed is increasing, then your kinetic energy is going to be increasing. If the speed is decreasing, then your kinetic energy is going to be decreasing. So that's one way of looking at it. And if your energy increases, your kinetic energy increases, that's a positive work being done. And then if your energy decreases, it's going to be negative.